So this week we're just focusing on one thing, and that one thing is titration. And titration is just a particular kind of limiting reactant stoichiometry. The goal is to get as many moles of acid as you have, the same moles of base. And when the moles of acid equals the moles of base, we're done and we do some calculations. I was talking with the person who's currently teaching 1B, and he was commenting on this semester, like they don't know how to titrate. They don't know what to do with the data. And I'm like, in 1B? And the reason is probably because they took 1A in the spring and they weren't on ground to do this. So anyway, it's important and it'll come back. And so now I'm gonna go ahead and share the screen and show you my notes. So hopefully you have them. I think that they will be helpful. Okay, so the first thing is we need a balanced chemical equation for an acid-base reaction. That's a double displacement reaction. There are three kinds of balanced reactions we do. We do a molecular reaction, and then a total ionic using the solubility table, and finally a net ionic. For this kind of problem, we always use the molecular, the complete reaction. So, sodium is group 1 metal. Group 1 metals make +1 ions. Hydroxide is one of the polyatomics that you need to memorize. They come together in a 1-to-1 ratio. Sulfuric acid, ic acids come from 8s. And because that 8 has a -2 charge, we need 2 hydrogen ions to balance it to make a compound that begins with H, which we name as an acid. This is a double displacement reaction. So we're going to let the cation of the first go with the anion of the second. And the anion of the second go with the cation of the first. We're making water. And so a good question would be, how many waters can we make? Well, one hydroxide here could make 1 water, but here I have 2 hydrogen ions. So if we put a 2 in front of sodium hydroxide, we can form 2 molecules of water. Hello, Romeo. Okay, so there's my balanced chemical equation. And that is the starting place. And what we're mostly interested in is this 2-to-1 ratio. And we're going to use that when we do the stoichiometry step. So this is the general idea of titration. The setup for general chemistry, and actually titration is done out in industry too, it's done other places, but the setup is always the same. We have a burette, and the burette is just a long glass tube, and we're going to put either the acid or the base in it, and then dispense into the flask that contains the other one. Typically, we would put the base in here. And the base, in our case, is sodium hydroxide. Typically, we would put the acid in here. And in our case, the acid would be sulfuric acid. Doesn't have to be that way, but when you read experiment 7, that's how it's described. However, for the problem that I'm going to do next, it looks like I put the base in the flask. So I'm going to go ahead and change that here to be consistent with the problem we're about to do. So I put some solid, some grams of base in a flask, and I put a solution that has sulfuric acid into the burette. And I'm going to dispense acid to base until I have an equal number of moles of acid as base. So the end point is when I stop adding from the burette. The end point is when I stop adding. The equivalence point is really the important point. For a titration, this is the important point, and that is when the moles of acid equals moles of base. Now, ideally, the equivalence point would happen, the end point would happen when the equivalence point happens. How do we do that in lab for experiment 7, for example? We use an indicator, and the indicator that we're using here is phenolphthalein. And phenolphthalein is colorless when the pH is less than or equal to, and they say 8 to 10. So when it's acidic. pH 7 is neutral, pH is less than 7 are acidic, but it goes from 7 to like 10 with just 1 drop of base, so it doesn't take much. And then it is pink when the pH is basic. So the way we have the drawing here shows that we would be starting with some sodium hydroxide. We're going to mass out a certain number of grams, and then we've added water so that it can dissolve and dissociate into the ions that it's made of, and then a little bit of indicator, maybe 2 or 3 drops, so that it's pink. And then the equivalence point will happen, the end point will happen when pink goes away, goes to colorless. The equivalence point happens if we can do that when the moles of acid match the moles of base. Okay, so what that means is for the thing that's in the burette, to find the volume, we have to find the volume by difference. If I start initially with some solution up here, and then I drain into the flask until pink goes to colorless, and I stop at that very moment, and then when I'm done and I stop adding to the flask, I have a final volume. I'm going to take my final, my initial minus my final to get the difference in volume, and that'll be the amount of acid, in this case, that I needed to add. So we do a subtraction step to find the change in volume, and that's the volume that we use for the calculations. So you'll notice after you do your pre-lab, when I post the data for you, when I attach it to your pre-lab work with your grade, that there's 2 volumes for every titration. Why? Because there's an initial volume and a final volume, and the difference in volume is the amount of titrant, whatever's in the burette, that has been added to the flask. So you have to subtract to find that. And then, and our goal is to just match moles of acid to moles of base, because that's the equivalence point. And the end point is when we stop adding. And the best titrations are when these 2 things happen at the same moment. We stop adding at the equivalence point. Okay, so in the lab that you're about to do, I'm going to clear this real quick. And when I say about to do, I mean on paper, we're going to work through experiment 7. The way that the setup goes in that lab for experiment 7 is that we have some concentration of hydroxide, and we don't know what it is. And so the goal of part B, in part A of the lab, you would be making your solution, which is going to be approximately 0.1 molar. So part A, we're not going to do because that would be you making your base. Part B is you using a known amount of an acid. So in here, we have oxalic acid. And you would mass that out in grams. And then you would add water and some indicator. And because you have acid in the flask, there would be no color. And then you would be trying to figure out by adding base to make it just barely pink, super light pink, and then subtracting your initial and final volumes. So you would be adding some base, and the goal is to figure out what the molarity of the base is. So part B, which is the data that you'll get right after you submit your pre-lab to me. Part B is for you to figure out what the concentration of hydroxide is. And then in part C, you're going to use the hydroxide, and you now know what the concentration is because you figured it out. Now you're going to have a mixture, and the mixture is going to have an acid that's called potassium hydrogen phthalate, KHP. It's an organic acid, plus some salt. And so in part C, the unknown part is how much of that mass that you put into that. So it's a mixture that is dry, solid, and you add water and you add phenolphthalein, but your goal is to figure out how much of what you put in actually was KHP, so you can come up with a percent composition of that mixture. And then in part D, you're going to be using that same concentration of hydroxide that you determined in part B, and this time you're going to have vinegar. And vinegar is a mixture of acetic acid and water with flavorings and other things. And your goal is to figure out what percent of that mixture, which is a liquid, is vinegar. And so this whole thing adds up to a lab that if we were on the ground, we would spend 3 weeks doing and calculating, because the skill of titrating, it is a skill. It takes practice, and students shoot past the endpoint all the time, and then you start to get better. But because we're not on ground, I'm just going to describe how it goes, and then there's some videos that you need to watch that Eric Yu, who is our Chem 1A instructor, he's made for this lab. And then we're just going to do the math part. Okay, so right now I'm just going to do a calculation that gets you through part B. And then as we meet throughout the week, I can do different calculations. I hope that you will let me know what you need, so that I can tailor how we spend our Zoom time to what you actually benefits you. So here we're going to start with some mass of sodium hydroxide, and that's going to be in the flask. And then you would add water, and the sodium hydroxide dissolves. And then we add some phenolphthalein, and now it's pink. And so I know what mass of sodium hydroxide I have in here because I mass it out. I put it into the flask using a balance. And then if we know the mass of sodium hydroxide, we can use the molar mass to get to the moles. If we have a balanced chemical equation, and we do, we can get from moles of base to moles of acid. And so in the burette, we would have the acid, and it would drop in, drop by drop, until the pink just went away. And then if I divide the moles of acid by the liters, which is going to be the initial volume minus the final volume, I can have moles per liter is molarity. I can know the molarity of the acid. And so that's what we're doing in this problem here. It says that 28.44 milliliters of solution was required to get to that place where moles of acid equals moles of base, which is what a titration is. And so down on the bottom, I have my roadmap, and I begin. In a separate step, I figured out the molar mass of sodium hydroxide is 40.00 grams per mole. And I want complete units, so I say moles of sodium hydroxide. And if I wanted to be, that's full credit. If I wanted to be super complete, I could put grams of sodium hydroxide down here. Why do I say that? Because I've started grading the lab exams, and units are a big deal. And now I'm going to use this 2-to-1 ratio from the balanced chemical equation, the molecular one, and say 2 moles of sodium hydroxide are required to neutralize every 1 mole of sulfuric acid. And then what volume was that contained in? 28.44 milliliters. Problem is, molarity is moles of one thing divided by liters that it was contained in solution. And so I need that in liters. The way I'm going to fix that here is instead of writing milliliters, I'm going to write times 10 to the negative 3 liters, because 10 to the negative 3 means milli. Okay, so sometimes it bothers students that I have nothing in the denominator here, and that in this dividing by the volume, I have nothing in the numerator there. If that's you, or if you're trying to manage your space, it is totally fine to take this number and stick it there. I'm not going to do that because I think the way I'm doing it matches my roadmap and makes logical sense. Okay, so I do that and I get my result. And I think I got 0.112122 molar sulfuric acid. So on this practice page, I've said, I did this 5 times and here are my 5 molarities. So I'm not including my example here. I'm just using the 5 things in the data that I give you, that I'm giving you on this page. And then our goal is to answer questions like, what is the mean? What is the mean deviation? What's the percent deviation? What's the standard deviation? And then report it, the average with the standard deviation. So that's my goal, is to answer those questions right now. I believe you already know this. So I'm not gonna, I've done all the work. What I'm gonna say is, I think you know how to find the deviation and the deviation squared because you've done standard deviations. So let me just remind you that once we come up with an average, the deviation is just an example, maybe trial 1's number minus the average. And so these deviations are going to have signs, positive or negative, depending on, is the trial 1 number larger than the average? Then it's positive. Is the trial 1 number less than the average? Then it's negative. And when we add all the deviations together, they should add to 0. If they don't add to 0, it's because we've done some rounding. We didn't keep everything on our calculator. If it adds to something that's very close to 0, you know, call it 0. That's fine. Okay, and then we square the deviations so that when we get a number here, we're adding things that are positive together. And then later for a standard deviation, we would take the square root of those deviations squared, dividing by n minus 1. So I think that you know how to fill in this table because you've done it for standard deviations a couple times in our class. So before I got here today, I went ahead and I filled in the table, and this is what I got. If you want to take a screenshot or a picture, that'd be totally fine, but this table is going to be on every page. So now I'm going to talk about what to do with those things. And I'm going to go through the steps, A, B, C, D, E. What are these things? First of all, what is the mean? The mean is just the average. When you report the mean, say on the lab that you're going to turn in a week, you need to make sure that you round it appropriately when you put a box around it and report it as an answer. But don't round other times. Notice that I'm carrying a lot of for everything I'm doing here, I'm carrying a lot of extra digits. I'm not going to round because I don't want to have a rounding error. But if the question says, what is the mean? I'm going to round to 4 sig figs. And then I'm going to say the mean. So I might say molarity and put a bar over the top to say average equals 0.112. I'm going to leave this as a 1 because it's followed by a 2, which means round to that number, and units. Put a box around it. There's the answer to A. The next one says, what's the mean deviation? And this is new. And so the deviation, mean means average. The average deviation is just the sum of all the deviations if they've been made positive, divided by the number of trials. So there's no n-1 going on here. It's just the average of the deviations. So what I need to do is to, for the ones that are negative, make them positive. And then I'm going to add them all together. And when I do that, I got 4.8656 times 10 to the negative 3. And the units are molar. And then all of these went, because a deviation is us subtracting this that went 4 past the decimal and this that went 4 past the decimal, and it's subtracting. I've marked where my deviations stop being significant, the last sig fig, and it's 4 past the decimal. And so for this number, that means it stops being significant at the 8. So I am following my sig figs as I add all these things together. And before I added them, I made them positive so they didn't add to 0. And now I'm going to divide by, I have 1, 2, 3, 4, 5 trials. Let me divide that by 5. Oops. I need to say what I have here. And what I have here is the mean deviation. Put a box around it because there's a lot of work on that page. Questions?
So you're essentially giving us all of the data because obviously we can't do this in person and we just have to work through everything, and you'll be checking our work as we turn everything in each day?
Exactly.
Okay.
So if we were doing this on the ground, once you had gathered your data, which is this mass and this volume, and you had used to calculate your molarities, you would have probably 5 molarities for the base that you made that's in the burette. And then I would need to see your 5 numbers because students will make mistakes calculating, but they need that number. The molarity is going to be used in part C and D. And so if they're wrong in part B, it leads to cascading errors. But I could just walk around and check with you. I can't do that online, which is why I'm going to have you turn it in to make sure you got the right number before I let you proceed. But yes, that's right, Marilyn.
Okay, thank you.
Yeah. Okay, and then if you've looked at the lab, you can see on pages, I think it's 9 and 10, it asks you, what is the mean deviation? What's the percent deviation? What's the standard deviation? That's why we're working through these calculations, because I can't put them on the whiteboard in the room. We're not in the room. Okay, so the things that I wanted to highlight here that I think are important, but sometimes get forgotten is when you report your answer, you start by stating what it is. The thing I'm reporting is, and then you give the number. And if there are units, and there usually are, you have to report the units too. And then the number has to be rounded to the correct degree of precision, which is based on the data that you have. But the rounding doesn't happen anywhere before you get to the final answer. So all the things I did to get to this number, to plug in this equation, to get to this number, they were not rounded on my calculator. I carried everything on my calculator. Why am I telling you this? Because I want you to understand for science, and I also want you to maximize your points. I don't want you to make the common mistakes. So that is a mean deviation. It just means average deviation. To do it, I had to change the deviations that were negative to positive so that I ended up with a sum that was greater than 0. The next question says, what is the percent deviation? And so what we're doing is we're comparing the deviation that we came up with to the molarity that we came up with. It gives us an idea of, for this thing I measured, how much off was I? Did I vary by a little percent? That's great. And so for percent deviation, I'm going to say, I'm not even sure how to say percent deviation, but I'm taking the mean deviation and I'm dividing it by the average molarity. And as soon as it says percent, that means multiply that by 100% or 1 in the form of 100 over 100. And that'll be our answer. So the mean deviation that I came up with on this page, I'm taking the one that has all the digits. I'm not rounding. And on my calculator, I had more digits. And then for the molarity, I'm going to use the molarity that is the average with extra digits, so I don't have rounding error. So this molarity and this molarity are going to cancel. The deviation was good to 7, and the average was good to this 1. So I have 2 sig figs divided by 4 sig figs times unlimited sig figs. Molarities mean I'm not going to have any units, which is kind of weird. That doesn't normally happen. But I get my answer. Once I get my answer, I round to the correct degree of precision. And then if I knew how to label it, if I had a symbol for it, I would use it, but I don't have a symbol for it. So I'm going to write percent deviation. To box around it.
Do you find that percent or that molarity divided by molarity in this step usually always cancels the unit out?
Here it does, because the molarity in the numerator is the molarity of sodium hydroxide, and the molarity, of sulfuric acid, and the molarity in the denominator is also the molarity of sulfuric acid. So because they're the molarity of the same thing, they canceled.
Okay.
Yeah, it's kind of like in empirical formula problems. When you have moles of oxygen over moles of cobalt, moles don't cancel because they're not actually the same kind of moles. But here, these are both molarity of sulfuric acid.
Okay, thank you.
Good question. If they didn't cancel, I would probably put parentheses here, and then I would have the thing on the top and the thing on the bottom to show what they were. So there would be a different way of writing the complete units in that case. Okay, the next one is, what is the standard deviation? And this you know how to do. Standard deviation is just going to be the square root of the numbers that have been squared and added together. So the sum of the deviations squared divided by n minus 1. And then some students, not you, because you're the good students who are here and paying attention, but students that don't watch the videos or don't pay attention, sometimes don't put n minus 1 there, they put n. And they're like, well, I saw it online, so it's right. It's not right. It's only right if it's only n if you have gotten a value for every trial that is possible. So if there were 5 objects that were made as replicates, and these are the only 5 of this kind of object in the world, and you found the density of each of them, but they were the only 5 in the entire world, you would divide by n. But if there's, 10 or 100 or 1,000 or 1,000,000 of these objects, and you found the density of 5, you divide by n minus 1. So do you have the whole set, divide by n, or do you have a sample set, divide by n minus 1? You have a sample set. So we have to divide by n minus 1, which may not be a problem for anybody I'm talking to here, but maybe in the video it will help somebody. Again, I'm rounding it to 5 sig figs here, but that's not what I had in my calculator. Oops. When I did it, I had more things in my calculator. Okay, so molarity squared, square rooted, ends up being molarity. It's a standard deviation, so I round to 1 sig fig. I'm either going to round up or round to even, but either way, that ends up being a 2. And it has the same units as the average. What is the purpose of the standard deviation? It's a way for us to know where to round our average. So the last one says, report the average molarity with its standard deviation. And because, so I'm going to do the molarity, average, plus or minus S, inside parentheses with units. And I'm going to call that the average. Because my plus or minus S ends in 3 past the decimal, this number is going to end at 3 past the decimal. Okay, so I want to point out that how we round for an average is different than how we round for a value. So all the values I've been talking about right now have been the molarity of a solution of sulfuric acid. And when I first started this, I said, we're going to titrate, and our goal is to figure out what the molarity of the stuff in the burette is. And here's some data. This has 4 sig figs. This has 4 sig figs. So it's 4 sig figs, and then my molar mass to 2 past the decimal, which is the periodic table I have, 4 sig figs. This ratio that came from the balanced chemical equation has unlimited sig figs. And then the volume here is 4 sig figs. So when I found for one sample what the molarity is, and I was reporting my answer, I would round, I should not have circled that. What I should have done is write molarity, no bar over the top, equals 0.1121 or sig figs molar. So I use the sig figs here to determine for an answer, one answer, what the molarity is. But when we have a group, when we're looking at an average, so there's several replicates, several trials of the same thing. Now, the standard deviation, which has 1 sig fig, its place value tells me where to round the average. It's a more sophisticated way of determining the number of sig figs in a value. We only do it when we have replicates and we have an average we're reporting. All righty, that's all I got there.